First, we revise vector space. V is a vector space over a field F. V is embedded with two operations, vector addition and scalar multiplication. Vector addition is a map from V cross V to F, and scalar multiplication is a map from V cross V to F. Now the properties satisfied by vector space are: first one is the associative property, that is, for any U, V and W belongs to V, U plus V plus W is same as U plus V plus W. That is, if we change the order of addition remains the same. Next property is the existence of identity. There exists additive identity 0 belongs to V such that U plus 0 equal to U. For next property is the additive inverse. For U belongs to V, there exists minus U belongs to V such that U added with minus U gives the additive identity 0. Next property is the commutative property, that is, addition is commutative in V. U plus V is same as V plus U. The next four properties are with respect to the scalar multiplication. When A distributed over U plus V gives you AU plus AV. A plus B operated on U gives you AU plus BU. That is, A plus BU equal to AU plus BU. Next, A dot B operated on U is same as A is operated on BU. Next property is the 1 dot U equal to U, where 1 belongs to field is the multiplicated identity in F. Next, we discuss what is a field. F plus dot is an algebraic structure. It is said to be a field when it satisfies the following property. First property is the closure property. Whenever AB belongs to F, it implies A plus B belongs to F. Second property is the associative property. A plus B plus C is same as A plus B plus C. Here A, B, C belongs to F. They are the elements of field F. Third property is the existence of identity. There exists 0 belongs to F such that 0 plus A is equal to A. Next property is the existence of inverse. For A in F, there exists minus A in F such that A plus minus A gives you the additive identity. Next property is the commutative property. A plus B is equal to B plus A. So these 5 property shows that F plus forms an abelian group with respect to operation plus. So F plus is an abelian group with respect to addition operation. The next properties are with respect to dot operation. The first property is the closure property, that is, A belongs to F, B belongs to F implies AB belongs to F. Second property is associative property with respect to dot. A BC is equal to AB applied on C is same. Next property is the identity property. There exists 1 belongs to F such that A dot 1 is equal to A. And the next property is for A non-zero. For any A belongs to F which is not equal to 0, there exists A inverse belongs to F such that A operated on A inverse gives you the identity element 1. Next property is the commutative property. A dot B gives you B dot A. With these 5 properties, F after exclusion of the 0 element forms an abelian group. So with these properties, 5 properties with respect to addition and these 5 properties with respect to multiplication. Here F is the whole group, or here we exclude the 0 because every non-zero element has a multiplicative inverse. Not every element. Every non-zero element has a multiplicative inverse. With these properties, F forms an algebraic structure with respect to two operation addition and dot, and this algebraic structure satisfying these 10 properties is called a field. If one more property called distributive property is satisfied, this property says when A is operated on B plus C, it gives AB plus AC. So with the distribution law, F plus dot, this algebraic structure forms a field, is a field. Here one point is very important, is that the closure property. This is the closure property and this is the closure property. Closure property with respect to addition and multiplication is embedded itself in the definition of the map. Actually, what is addition here? Addition is a map from F cross F to F. This map itself defines any two element A, B belongs to F cross F, gives you A plus B, and A plus B is a member of F. So this is same as AB belongs to F gives you A plus B belongs to F. Closure property, it's satisfied by the definition of the addition, and similarly multiplication is again a map F cross F to F. So A B maps to A dot B. So again this is the closure property with respect to multiplication. So whether we mention these property, if we do not mention these properties, then again it is okay, because these two properties are embedded in the definition of the operation addition and multiplication. So now you clearly understand what is field. Next we see how R square with respect to two operations addition and vector multiplication forms a vector space. Let us see how all these properties of vector space are satisfied in R square. First we see how the elements of R square looks. R square means R cross R. It means its elements are of the form x comma y, that is, it is an ordered pair x comma y where x belongs to R and again y belongs to R. So the elements of R square are of the form x comma y. Now how these elements perform vector addition and scalar multiplication? Vector addition in R square is defined as if two elements x1 and y1 and x2 and y2 added, then they are added component wise, that is x1 added in x2 and y1 and y2 are added, y1 plus y2. You again see this belongs to R and this belongs to R because R plus is a group, that is if x1 belongs to R and y1 belongs to R, then x1 plus y1 belongs to R. So x1 plus x2, because x1 is an element of R, x2 is an element of R, therefore x1 plus x2 belongs to R and y1 plus y2 belongs to R. So finally this element x1 plus x2 and y1 plus y2 belongs to R cross R. Scalar product A operated on x1 comma y1 gives you the component wise multiplication, that is A is operated on the first component and A operated on the second component, gives you the ordered pair AX1 and AY1. This belongs to R cross R. So the two operations, vector addition and scalar multiplication, is defined here. Now we will see कि with these two operations R square forms a vector space or not. So the first property is the closure property. This is obviously satisfied when two elements, one this and second element this, when two elements are added, then they belongs to R square. So second property is the associativity. You can check that any three element x1 y1 plus x2 y2 and x3 y3, these three elements, if you change the order of the addition, then this gives you, I am writing here the final result, x1 plus x2 y1 plus y2, and then this is added in x3 and y3. This gives you x1 plus x2 gives x3 comma y1 plus y2 plus y3. Gives you. Now you can change here the associative property. You apply here the associative property, x1 plus x2 plus x3 comma y1 plus y2 plus y3. This gives you x1 comma y1 plus x2 plus x3 comma y2 plus y3, and this gives you x1 y1 plus x2 y2 plus x3 y3. So in this way you can see if u plus v is added to the third element w is same as u added to v plus w. So this is the associative property. Third one is the identity property. Obviously there exists 0 0 belongs to R square such that for any xy belongs to R square, xy added to the additive identity gives you the same element. Hence this is the identity element in R square. Fourth property is the existence of inverse. Obviously for xy belongs to R square, there exists minus x minus y belongs to R square such that xy added to minus x minus y gives you x plus minus x and y plus minus y, and this gives you the additive identity 0, 0. Fifth property is the commutativity. For any two element x1 y1 added to x2 y2 gives you x1 plus x2 comma y1 plus y2. Now we can change this order. We write it as a x2 plus x1 and y2 plus y1. Why? Because R with respect to plus forms a commutative group with respect to addition. That is, the commutative property hold in R. Here we discuss the commutative property in R square, and here we make use of the commutative property of R. This is equal to x2 y2 added to x1 y1. So u plus v gives you v plus u. So this is the commutative property satisfied in R square. So R square with respect to plus operation forms an abelian group. One point is important, that is whether we have to show the closure property or not. So closure property is already embedded in the definition, so we need not show it here. We simply start with the associative property and identity property, and then existence of inverse, and then the fourth property commutative property. So with these properties, R square plus forms an abelian group. Next properties are with respect to scalar multiplication. So first property is A operated on u plus v gives you au plus av. So A is the element of R here, because R is a field of real number, and u is the element x1 y1, and v is the element x2 y2 belongs to R square. These two elements u and v belongs to R square. Now A operated on u plus v means x1 y1 plus x2 y2. It gives you a operated on, first we operate these two. So x1 plus x2 comma y1 plus y2. That is, this operation is taken place component wise, that x1 is added x2 and y1 is added into y2. So a is operated on x1 plus x2 comma y1 plus y2. So a is multiplied inside a operated on x1 plus x2 comma a operated on y1 plus y2. This gives you a x1 plus a x2. This gives you a y1 plus a y2. Here I am using the distributing property of the space R, because R plus is itself R plus with R with plus and dot itself a vector space. So ax plus ax2 comma ay1 plus ay2. This is equal to ax1 comma ai1 plus ax2 ay2. Now in this line we separate the components. Now this is same as a is operated on x1 y1 plus a is operated on x2 y2. So a distribute over these two components, that is a u plus v gives you au plus av. This is the first property. The next one, a plus b operated on u gives you au plus bu. Again a and b belongs to R and u, that is xy, belongs to R square. Remember, a and b are the members of field and u is the member of the vector space V. Now a plus b xy gives you a plus b operated on x comma a plus b operated on y. This gives you ax plus bx comma ay plus by. Again we separate component ax ay plus bx by. This gives you a xy plus b xy. So this element v so x comma y, this element of R square distribute over a plus b. So this is the second property with respect to multiplication, and it is satisfied. Next property is a dot b u is same as a operated on bu. It is not necessary to put dot here. So again let a and b belongs to f and u as xy is a member of R square. Now a b u means a b operated on x comma y. This gives you a b operated on x comma a b operated on y. This is equal to a bx comma a by. may be written as A operated on Bx and A operated on By, because R plus dot is a vector space. It satisfies this property A Bx equal to A dot Bx. Again, this is A operated on Bx By, and again this is equal to A operated on B x y. This gives you A B U. The next property is 1 dot U is equal to U. It is simple. 1 belongs to F and U as an xy belongs to R square. So when 1 operated on U means 1 applied on xy gives you 1x comma 1y. This is x y, and this may be written as 1 operated on xy. So no need to write this because we have to prove this. This is U. 1 dot U is equal to U. So this is the last property with respect to vector space. So all these properties with respect to scalar multiplication and these properties with respect to vector addition are satisfied with this space R square. So R square is a vector space over the field of real number. Now it is clear that how you can prove a space, any space V with respect to two operations forms a vector space. You need to satisfy all these properties of the vector space one by one. If you practiced, it will not take long time to solve these questions. Similarly, you can solve Rn over R. Rn is a space. Rn is a vector space over the field of real number. How the components of Rn looks? Rn contains the n tuple x1, x2, xn. This elements belongs to Rn. You may try to prove this as in case of R square. R square contains the two tuple, that is x1 comma x2 type, but Rn contains the n tuple. It has a component x1, x2, xn, and the addition is performed like this. If two tuples, x tuple and y tuple, here yn are added, then component wise addition, x1 plus y1, x2 plus y2 and xn plus yn. Similarly, when a scalar is multiplied x1, x2, xn, it gives ax1, ax2, that is component wise multiplication, comma axn. So with this tuple operations, how this tuple works in scalar addition and vector multiplication, we can prove that Rn is a vector space over the field of real number.